Good afternoon, all. So my name is Pandarasamy Arjunan. So this is a joint work with some of the folks at IBM Research Bangalore and my advisors Amarjit Singh and Pushpendra Singh. So today I'm going to talk about a piece of work called multi-user energy consumption monitoring and anomaly detection using partial context information. So we all are at BuildSys because we all folks are interested in energy. And if you look at overall, buildings are one of the largest energy consumer around the world. And in order to reduce the energy usage, so at least in this decade, there are a lot of smart meters have been installed. So if you look at the scale, there are a lot of millions and millions of meters are installed around the world. And so typically they measure the energy usage every 50 minutes to 1 hour interval. And using this energy metadata, there are a lot of energy monitoring and optimization applications and a lot of research sources going on. So in this regard, this is one of the enabling technology for monitoring fine-grained energy usage in these buildings. But let's look at a view of how this energy data looks like in a larger setting. So this is an energy usage pattern of a commercial building. So as you for an year, just to make you understand, in the x-axis you have the day of the year, and in this y-axis you have the hour of the day, and each small cell corresponds to the intensity of the energy usage of that particular hour. So that is averaged over. As you see, there are a lot of common usage patterns, like we have fixed daily and weekly energy usage patterns in this building. So mostly this is weekdays, weekends, and there is a fixed schedule going on from morning to evening. And there are some seasonal changes. So I think this is during some summer. This is a building in Sweden. There is summer, there are less energy consumption because this is actually a school building, and it seems those some of the components are turned off. And during winters, so it seems they had turned on some components, that there is some increased energy usage. I think there is some break time. I think this is, if you look at this pattern, it seems there are some components were turned on during the night hours and also during the weekends. So this could be a potential anomaly energy usage events. If you just look at only this building energy meter data, or if you apply any standard anomaly detection method that is proposed in the literature, probably that algorithm will tag this day as a possible anomaly usage. But if you look at other meters or other neighboring buildings within the campus, so probably this may not be looking an anomaly because there is some common, there is some function or some festival is going during this time. This may not be a potential anomaly usage. And also if you see, this can be potential anomaly usage. In this case, there is some changes. Abnormal usage only in this building. It is not reflected in other buildings, and this also could be a potential anomaly usages. So the point here is actually this energy usage is actually impacted by several context variables like occupancy, seasonal patterns, some rare events, and so and so. But if you want to do some anomaly detection, so this context information will be really useful to fine-grainedly locate the very specific anomaly usage. But collecting all those context information is very non-trivial. So we need to put some additional infrastructure, and it incurs a lot of cost and management efforts. So the point is, can we use some readily available meta information? And so in the previous session, we were talking a lot about the metadata. Can we use some of the readily available meta data that is, that anyway it's there in the electricity meter to improve this, anomaly detection methods? So that's a talk I'm going to present. So the problem definition is actually identifying potential anomaly energy usage events using the hourly energy meter data, but using only the hourly meter data and some available meta information. And you'll get the anomaly score day wise. So the interested context information, the meta information that is interested on this work is actually only the timestamp. So it is very common for because basically these meter readings are actually a time series, and the location information, particularly where these meters are installed. So The reason we are interested on this temporal timestamp is actually there are a lot of temporal context, as I explained, the daily usage, weekly usage, and the hourly usage, and the seasonal information. All those context information can be extracted from this timestamp itself, right? And this location information is very important. If you have if there are some unknown context events, like some rare events, as I was showing in this figure, right? There are some rare events that is happening, but that is reflected in all the buildings, and this individually all those buildings comes under same functional or administrative neighborhood. Then probably you can use that information, neighborhood information, as a context variable to to assign different anomaly score for those factors. So in this work, actually, we are assuming that this location information is there, and this neighborhood information is also provided by some domain expert, or there are some existing methods that we can use to extract neighborhood information. So let's look at how this system looks like. So particularly, you have a meter data coming from a particular building. And so you first split that metadata into different some temporal context set. So you may have a set of context set, or you may have a multiple context set, and later you can combine them. And for each context set separately, you'll apply a anomaly detection algorithm, and that score is called a self anomaly score. And you repeat this for all the meters in that particular neighborhood, and you'll get a self anomaly score for all the meters, or that means all the buildings in a commercial complex or anything. Okay, and then using the neighborhood information, and particularly the baseline correlation of these buildings, so you can adjust this scores, adjust this anomaly score for some unknown some rare anomalous events. So after this, you will be getting the adjusted anomaly score. This is the overall picture of the method. Now let's get into this algorithm, how these 3 steps are working. The first step is actually splitting into different temporal context sets. So in this work, actually, we are considering 3 basic temporal context sets, that is weekday, daytime, weekday, nighttime, and weekends. And so this is a very simple context, temporal context sets, but that is what we had observed in the data. And so after that, we are computing the self anomaly score algorithm. So the algorithm flows like this. So given a time slot for a particular temporal context sets, so first what you are doing is actually we create a dissimilarity matrix. So this dissimilarity matrix, it's a metric to identify how close these time slots are, to identify the anomaly. So for that, we are using a TDW, dynamic time warping function, because this is, if there is a time sheet in the data, this will take care of that. And then we apply some outlier detection algorithms. So this will, so for each data point, it will assign a score. Among the score, we can set some threshold to select these are the potential anomaly events, and those events can be given to the facility manager, and in further they can look into this anomaly score. So the more details of this algorithm is present, it's given in the paper. For the sake of time, I'm not explaining all this. And the next step is actually using the neighborhood information. So we need to adjust the self anomaly score. The way we are doing is actually, so for a self anomaly score, it's minus, you assign some weightage for the neighbors, because this weightage is based upon the baseline correlation. So if, let's say there are 2 buildings, these 2 buildings are having similar usage pattern, then probably you'll assign the correlation will be high. So and accordingly, and if other building has not so highly correlated, then probably that will having a less correlation. So you assign some weightage for each correlation, and accordingly calculate this adjusted anomaly score. So we implemented this algorithm, and we have experimented this in a diverse data set. So one is the commercial data set from Sweden, and there is another one from residential from India. So the building type is actually, it's a school campus. This is a residential apartment where a lot of working professionals are living. So particularly, so in this school we have about 10 blocks, sub-blocks, and they are mostly it is used for classrooms, office space, and mostly some fixed schedule. But in case the residential, it's family and somewhat irregular schedule. In the commercial, we had lighting, air conditioning, and a lot of office equipments. So in the residential setting, we have mostly the household appliances. So the data was collected for about 3 years, and in this case, it was collected for about 1 to 10 minute intervals, and there was some missing value sets. So in the residential setting, so it was collected for about 2 years. It was sampled at about 30 to 60 seconds, but for our experiment and for comparing our method with an existing method, we downsampled this to a 1 hour resolution, and that's the objective of this work. And this is the experimental setup. So one of the problem, one of the challenge with any anomaly detection method is actually collecting the ground truth information. And it's very difficult and it's very expensive to collect all the fine-grained ground truth information about all the anomalies, or otherwise we need to synthetically inject some anomalies. So in case of commercial building, the Sweden one, we asked the data owner for some portion of the meters, we asked them to be visually given the data, and we asked them to annotate whether this looks like some particular event. He went back and referred some logs to identify whether there is an anomaly or there is some normal genuine activity. In case of residential setting, we injected some known anomalies, and it is little very difficult to actually annotate that, so we injected some anomalies. So for the experiments, we use these 3 temporal context sets. The neighborhood information, as I mentioned, it's provided by a domain expert, or it can be extracted from some existing methods. So if we compare this method with the 3 baseline methods, the first one is the self-anomaly, that is anomaly detection method without using any context information as such. And the second one is actually using the temporal context information. And the third one is actually there was an anomaly detection method proposed by HP, and that appeared in, I think, 2009 BuildSys. So they also did this experiment for a commercial building, and they were also using a 1 hour resolution data for identifying the anomaly. So we are comparing our method with this HP's method, and also we don't have much anomaly cases to present this result in case of true positive and false positives. So we are analyzing the result as a case by cases. So we take one particular anomaly. For that we have some information about what is going on, and we are see how these things work. So this is the commercial building. So this is the actual meter data. So from August 13 to August 14 in 1 year. So these are some potential anomaly usage events that we know. So this is how the self-anomaly detection algorithm that we had proposed is working. So it is able to detect this portion as an anomaly. And this is after using the temporal context, since we had used 3 contexts. So during the night time and the daytime and the weekends. So for each time slot, it is assigning the score. And this is after adjustment. And then we have the score for the HP as well. So let's look at this, what's happening here. So particularly for this case, the self-anomaly score it's able to tag these portions. And for using temporal context, it is actually improving that here. But using this adjustment, neighborhood adjustment, it is actually decreasing a bit because the weight was adjusted using the correlation of other meters. In that, they were highly correlated with this, but this portion is not having the anomaly, so it is actually adjusting a bit actually. And this is a core score for the HP's method, and it is assigning high score, but there are other cases it failed actually. So there are other details about this experiments, those are in paper. This is just one case how this algorithm works. So the reason, if you look at the baseline correlation, so mostly all these 8 meters, so they are highly correlated. So as you see, the lowest correlation is actually 0.74, the highest one is about 0.96. So the interesting thing is really to identify so how this temporal context, to what extent this temporal context and this neighborhood adjustment is helping the algorithm to improve the accuracy. So this is the plot of self-anomaly score without context and using the temporal context. As you this spread of this plot indicates so how much this temporal context information is useful to either some portion, some slot it is to increase the accuracy or decrease the accuracy. And this is the another case. So where we have the comparison between self anomaly score using the temporal context and this anomaly score, adjusted anomaly score. As you see, this plot is actually moving down. So there are many cases actually it is trying to assign lower score. And if you ask what weightage we should give for the neighbors, right? So this question can be answered by a domain expert who knew about this building operations, or it can be empirically evaluated. So in our case, we did, we assigned different weightage for the neighbors. So accordingly, this violin plot is showing that. So when I assign in 10%, okay, the anomaly score difference, that is self and the adjust score difference is very minute. As we increase the weightage, actually, it is assigning more. It is adjusting more actually. But if you look at this red point, this is the average score, average difference. So as you see, it is keep on increasing, but over the period of time. So after assigning 70% of weight, it starts to decrease the anomaly scores. So probably this will be an indicator for this particular data set. So about 70% of weightage can be given to the neighbors. And this is the result for a residential building. So relatively compared to a commercial building, residential building, we didn't have that much baseline correlation and also not that much regular usage pattern. And this is one example of an injected anomaly and how this algorithm works. And this is the baseline correlation among these residential buildings. As you see, the correlation, the highest possible correlation is about 0.76, and there are even some cases there are some negative correlations. And that's why, particularly for residential setting, it's not adjusting that much. And this is the same plot when we plot the self anomaly score without context and the anomaly score with using context. This is a very clear indication where this algorithm is performing not so good. The reason is actually the diversity of the usage pattern among the residential building usage, because this the adjustment factor is very narrow here. And this is the same violent plot. In this case, actually, even we are assigned different way, it is not saturating anymore. And this difference is also it's very minute actually. So it's hardly 0.5, 0.6. So in this work, so we presented an anomaly detection method using the partial context information, particularly only using the timestamp and the location information, to account for the temporal and for rare events that may affect multiple buildings. The usage of temporal context and this neighborhood-based adjustment is actually improving the detection accuracy, particularly when we want to include some context information. And it actually relatively works better for the commercial buildings than the residentials. The reason being, the residential buildings, we don't have that much fixed schedule by the occupants, particularly for the data set we had used. Thank you.